Welcome back to the deep dive, everybody. Today, we're diving into a pretty fascinating area, something that brings together our senses and abstract thinking, and that's the role of visual thinking in mathematics.
Ooh, that's an interesting one.
Yeah. When a lot of people think of math, they think of symbols and equations and pure logic. But what about when we bring in our ability to see, to visualize? What can we really do with that, and where does it maybe fall short when we try to use our vision to understand mathematical truths?
It's a question that has been debated for centuries.
Yeah.
And so, for some people who really are steeped in the kind of elegant symbolic language of math, the idea of relying on something like vision, something that seems, a little bit more subjective maybe, can seem almost radical, right?
Right.
But as we'll see in this deep dive, and we're drawing on excerpts from the Stanford Encyclopedia of Philosophy entry on the epistemology of visual thinking in mathematics, this back and forth between our visual sense and mathematical understanding and proof and discovery is pretty profound and surprisingly complex.
Yeah. And right off the bat, our source highlights a pretty interesting tension, something that I think should immediately grab you, our listener, especially if you're, maybe a philosophy fan or you've thought about the nature of intuition versus knowledge. Thinkers like Kant and Gauss thought that a kind of visual intuition, they called it Anschaum, was really key to getting math, to understanding it. And it wasn't just passively seeing, it was this interplay of perception and imagination. So, what we see with our eyes and then what we can imagine based on that, And that right away sets up a conflict because, as we'll see, some later mathematicians really wanted to base math on logic alone without this visual piece.
Yeah. And, those early figures, they saw Anschaum. And this included both sensory perception, what we actually see, as well as this imaginative visualization. They saw this as fundamental to having mathematical insight, almost like you were apprehending a mathematical object directly.
Right.
But then the 19th century saw a real pushback against that. And you have figures like Pasch and Hilbert, Dedekind, and even Bertrand Russell, who really wanted to put math on much firmer footing, where proofs would stand on logic alone, independent of any kind of visual aids. In fact, Russell famously said, "In the best books, there are no figures at all."
It's like they were trying to purify math, get rid of anything that couldn't be, boiled down to symbols and reasoning.
Mm-hmm.
And the concern was that relying on vision, on intuition, maybe that opens you up to vagueness, to
Right.
not really being sure. They wanted a foundation built on carefully defined terms and logical steps,
Yeah. And they worried that visual intuition, while it might help you see things, could also be misleading. It could lead you to conclusions that actually weren't logically sound. But then, as the 20th century rolled around, things started to change. People like Mancuso and Fomenko and Needham, they started saying, hey, visualization is really important in math. I mean, even the titles of their works, like Visual Geometry and Topology, show how they deliberately wanted to bring back the visual element to math.
It's almost like a pendulum swinging back and forth.
Yeah, absolutely.
Between these different views on what's the right way to do math or think about it even.
Exactly.
So here we are still grappling with these basic questions. How do we know what we know in mathematics?
Yeah.
And that's the mission of this deep dive, to unpack the epistemology, how we know what we know when it comes to visual thinking in math. Can a picture actually be a proof? How does visualizing help us discover new mathematical ideas? And, for our philosophy fans out there, what does all of this tell us about whether mathematical knowledge is a priori, known independently of experience, or a posteriori, known through experience? And keep those two ideas in mind, dear listener, because as we go, you'll see how thinking about math visually might push us in one direction or the other.
Exactly. So let's just jump right in with a big question. Can a picture function as a proof in mathematics?
Oh, here we go.
While some people might feel like a good diagram shows you something's true, a lot of mathematicians are still skeptical.
Yeah.
Even people who make those cool collections of proofs without words, they usually admit that those are more like visual arguments, not strict proofs in the logical sense.
Right. And then at the other extreme, you have people like Tennant, who said that a proof is nothing but a syntactic object, just a bunch of sentences arranged in a certain way based on formal rules.
Right.
So for him, visuals have no place in a proof at all.
Yeah. But the most interesting and maybe the most productive part of this whole discussion is the idea that visual representations can play a role in the reasoning within a proof. It's not that a diagram replaces the whole logical structure.
Right.
It's more that it's a key part of how we understand and check the steps in a rigorous argument.
Okay, so our source makes this distinction between replaceable and superfluous thinking when it comes to proofs. And for us philosophy folks, that's really important. So could you break that down for us a bit?
So imagine you're working through a proof. There might be times when you picture a shape or a diagram. If that visual thinking is replaceable, it means you could have understood the same thing and followed the same logical steps using something else, like just symbols or words, without changing the core of the proof. And if it's superfluous, it means you could have skipped that visual step entirely and the proof would still be fine. It might have helped you understand it better, but it wasn't strictly needed. So the big philosophical question is, can visual thinking ever be essential, neither superfluous nor replaceable, when we try to prove something in math?
And that makes the question of reliability even more important, doesn't it? If diagrams can be misleading, then how can they be a solid basis for proof, which needs to be certain?
Right. But, our source points out that we now have these things called formal diagrammatic systems.
Okay.
And these are not your typical sketches on a napkin. They're systems where the diagrams themselves are the basic elements, like the words in a sentence, and the rules of inference involve changing these diagrams in very specific ways. What's philosophically interesting here is that the soundness of some of these systems, the guarantee that they only lead to true conclusions, has been proven using non-visual, usually symbolic methods.
So if you have a system where you're going from one diagram to another, following specific rules, and we know the whole system is logically sound, then the visual steps aren't really superfluous, right?
Yeah.
You're manipulating the diagrams to get to your conclusion.
Exactly.
That's pretty neat.
Yeah. And the source gives a great example, Euclid's very first theorem, about constructing an equilateral triangle on a line segment. There's this guy, Miller, who showed how this proof can be done in a formal diagrammatic system. And when you think about that proof, you have to use diagrams.
You can't just talk your way through it.
You can't. It's essential. And this kind of throws a wrench into Tennant's idea of proofs being just sentences.
Right, because a proof isn't just a random string of symbols. It has to be interpreted. It has to refer to mathematical objects. And you need to show that the system you're using to get from one step to the next is sound. And in these diagram systems, the diagrams are the sentences, and changing them is how you do the logic.
Exactly. So while a proof might not be purely visual, and the idea that proofs are just symbols isn't perfect either, visual thinking, when it's part of a well-defined diagrammatic system, can be a real part of a mathematical proof.
So that addresses the reliability issue by grounding the visuals in a system we know is sound. But what about when mathematicians use diagrams in their everyday work outside of these very formal systems? There's still that feeling that they might not always be reliable.
Yeah. And there's good reason for that. The source talks about the unfaithful diagram, where your drawing accidentally includes things that aren't actually part of the problem.
Right, like those classic trick proofs where you end up proving that all triangles are isosceles.
Exactly. But our source says that these kinds of mistakes, while they happen, can often be avoided if you're careful.
It's like the diagram is tripping you.
Yeah. But the bigger problem is what they call indiscreteness of diagrams.
Okay.
Words can be super precise, giving you only the information you need. But a visual representation almost always gives you more information than is logically necessary. Like if you're told, let ABC be a triangle, and you draw one, your triangle will have specific angles, even though that wasn't specified.
So you're adding details that aren't really there in the original definition.
Right. And this can lead to what the source calls unwarranted generalization. You might base your reasoning on something you see in the diagram, but that thing might not be true for all triangles or whatever mathematical object you're looking at.
Right, so you might think something is true in general when it's only true for the specific picture you drew.
Exactly. They use the example of dot diagrams for triangular numbers, those patterns of dots arranged in triangles.
Yeah.
If you look at the pattern for, say, 6 dots, you might think you've figured out a general formula. But the diagram only shows you that one specific case.
So how do we go from seeing a pattern in a picture to saying it's a universal mathematical truth? Seems a bit risky.
It is. The source compares this to what happens when you're reasoning with symbols. When you say something holds for any arbitrary thing, you usually have to check that you haven't relied on some specific feature of that thing that isn't true in general. But with diagrams, that check is much harder. You have to be very aware of whether what you're seeing is truly universal or just an accident of the specific picture you drew.
And this triangular number example shows this, right? Because if you look at the pattern for one dot, it doesn't really look like a triangle at all.
Exactly. And this shows the danger of missing those edge cases when we rely too much on visual intuition from just one example. They also talk about Euler's formula for polyhedra, which ran into problems when mathematicians started looking at shapes that weren't convex.
Right.
And then there's Cauchy's attempt to prove something about convex polygons, which turned out to be wrong because the polygons could actually change from being convex to concave during the process he was considering.
So it seems like visual arguments outside of those formal systems can be great for getting ideas and making guesses, but they don't always have the same level of certainty as a formal proof.
Right. But the source is careful to say that visual thinking can still be part of proving things. They give this really cool example from knot theory.
Knot theory, like tying knots.
Sort of. In math, a knot is like a closed loop in space that doesn't intersect itself.
Correct.
And two knots are considered the same if you can deform one into the other without cutting or gluing.
Like untangling a piece of string, but the ends are always connected.
Exactly. And we often draw these knots as flat diagrams. And the big question is, can you tell if two different diagrams represent the same knot? Or if a knot can be untangled into the simplest knot, the unknot, which is just a circle.
So where does visual thinking come in?
Well, one way to show that a knot is the same as the unknot is to use these things called Rademacher moves.
Okay.
They're like specific ways you can change a diagram without changing the actual knot it represents. If you can get from one diagram to another using these moves, then the knots are the same. And this is visual. You can see the knot being untangled.
Like a visual demonstration.
Yeah. But the cool example they give is how to prove that a certain knot, the trefoil knot, which has 3 lobes, is not the same as the unknot. And this uses the idea of knot colorability.
Colorability sounds visual.
It is. You can color a knot diagram with 3 colors, following certain rules.
Okay.
And if you can color a knot diagram in this way, then any diagram for that same knot can also be colored. It's a property of the knot itself, not just the way you draw it.
Got it.
Now, the unknot can't be colored this way.
Because it's just one loop, you can't use 3 colors.
Exactly. But if you look at a diagram of the trefoil knot, you can see that it can be colored. So since the trefoil can be colored and the unknot can't, and this colorability thing is a property of the knot itself, the trefoil can't be the same as the unknot.
That's so cool.
It is. And the key part here is that you have to visually check that the trefoil can be colored.
You can't just argue about it abstractly.
Right. So this is a real visual proof, even though it's not using symbols or formulas.
That's a great example of how visual reasoning can be both essential and rigorous. Now, the source also talks about a debate about using diagrams in proofs in analysis, especially because it deals with things like infinity, which are hard to picture accurately. They mentioned Bolzano, who was skeptical about using visual intuition to prove the intermediate value theorem.
Yeah, the IVT, as it's known. This theorem says that if you have a continuous function, and it's positive at one point and negative at another, it has to cross 0, somewhere in between.
Right, like its graph has to cross the x-axis.
Exactly. And Bolzano felt that visualizing this wasn't rigorous enough. He wanted a purely analytic proof, using symbols and logic.
Makes sense. But then they talk about this guy, James Robert Brown, who challenged that view, right?
Yeah. Brown argues that we can be pretty sure the IVT is true just by looking at the graph of a continuous function going from below to above the x-axis. He thinks our visual intuition here is so strong that it's almost like we just know it's true. He even says that Bolzano's proof wasn't really proving the IVT, but rather proving a property of the real numbers that's needed for the standard proof of the IVT.
Whoa. So he's saying that maybe our visual intuition is more fundamental than the stuff we use to prove it formally?
That's his argument.
Pretty bold. So what do people say against Brown's view?
Well, there's this guy, Giaquinto, who critiques it pretty thoroughly. He says that when we think we're proving the IVT by looking at a graph, we're actually making a bunch of assumptions that link what we see to the formal definitions. And he says those assumptions aren't always true.
Like what?
For example, we might assume that if a function is continuous in the mathematical sense, its graph will look like a smooth curve.
Right, that makes sense.
But there are functions that are continuous, but their graphs are super weird and jagged.
Oh, wow. So what we see might not match the mathematical definition.
Exactly. Another assumption is that if a curve crosses the x-axis, it must have a value of 0 at that point. But Giaquinto uses the example of a function on the rational numbers, where the graph looks like it crosses the axis, but there's actually no rational number where the function equals 0.
Tricky. So you might see a crossing, but there might not actually be a point there.
Right. It all depends on the properties of the number system you're working with. And this raises a big question. Are there any theorems in analysis that can be proven just with diagrams?
Hmm. Good question.
And if so, what would those theorems be like?
Right. Can we find a whole class of them?
Yeah. And the source points to an area called O-minimal structures as a possible place to look. These are like carefully designed sets of functions that avoid those weird, unintuitive cases.
So maybe in these structures, the IVT could be proven visually.
It's possible. It's still an open question.
That's fascinating. It really shows how subtle this whole thing with visual intuition and formal proofs is. Now, the source also says that visual thinking might be even more important for discovering new math than for proving it. And they talk about 3 kinds of discovery: discovering new facts, discovering ways to prove things, and discovering new kinds of mathematical objects. Let's start with discovering new facts.
Okay, so in this context, discovering a fact means figuring it out on your own, not being told it.
Right.
And the difference between discovery and proof is that with a proof, you have to be very clear about the logical steps and why they're valid. But with discovery, you might just have a feeling that something's true based on what you've observed.
So how does visualizing help us discover new math facts?
Sometimes when you combine visual thinking with what you already know about math, you can come up with a visual argument that suggests a fact is true, even if it's not a formal proof. The source gives a classic example. The visual proof of the arithmetic geometric mean inequality. It's a diagram with 2 circles and a right triangle.
Oh, yeah, I've seen those. You use the lengths of some of the lines in Pythagoras' theorem, right?
Exactly. And you can see from the diagram that the geometric mean of 2 numbers is always less than or equal to their arithmetic mean. And by imagining how the diagram changes as you change the sizes of the circles, you get a strong feeling that this is always true.
So even though that imagining step isn't a formal logical deduction, it can still lead you to a true mathematical fact.
Right. It gives you confidence that it's true, and it might motivate you to find a formal proof.
Now, what about discovering ways to prove things? How does visual thinking help with that?
Well, it can give you the main idea for a proof. You might see something in a diagram that suggests a key assumption you need to make, or it might give you an idea for the steps in the proof. But the source warns that you can't just assume that what you see in the diagram is the proof. You have to carefully justify all the steps.
So the diagram is like a roadmap, but you still have to do the driving.
Yeah. They give an example of trying to find the minimum value of an expression. Looking at the graph might make you think you know where the minimum is, but just seeing it in the picture isn't a proof.
Right.
You still need to prove it formally. But the picture gives you a place to start. They also give an example from free probability theory, where looking at diagrams helps mathematicians figure out how to prove a certain lemma.
So even in very abstract math, visualizations can be super helpful for finding proofs. Now, what about the last kind of discovery? Discovering new properties or even new kinds of mathematical objects?
That's where things get really interesting. The source talks about geometric group theory as a great example.
Geometric group theory, that's where you combine algebra and geometry, right?
Exactly. And a key idea in this area is to represent groups, which are algebraic objects, as geometric objects called Cayley graphs. So you basically draw a picture of the group, and each point in the picture represents an element of the group, and the lines connecting them represent the group operation. They give examples of Cayley graphs for different groups, including the symmetric group on 3 elements and the group of integers under addition.
So by looking at these pictures, you can start to see geometric patterns in the group, even though it's defined algebraically.
Exactly. And this led mathematicians to think of groups as metric spaces, meaning spaces where you can measure distances between points.
Yeah.
You can do this on a Cayley graph by looking at the shortest path between 2 points. And while you don't need a Cayley graph to do this, thinking about them visually helped mathematicians develop this whole new way of looking at groups.
Like it shifted their perspective.
Yeah. And then they start thinking about what happens when you zoom out on a Cayley graph and just look at its overall shape, ignoring the individual points and lines.
Yeah.
And this led to the idea of quasi-isometry, which is a way of saying that 2 metric spaces are basically the same on a large scale, even if they look different up close. And it turns out that different Cayley graphs for the same group are always quasi-isometric.
Ugh.
So if a property of a group is preserved by quasi-isometry, it's a fundamental property of the group itself, not just of a particular Cayley graph.
Interesting.
And then they connected this to hyperbolic geometry.
Okay.
You know, that weird, non-Euclidean geometry where parallel lines can meet.
Yeah.
Well, in hyperbolic geometry, all triangles are thin in a certain way.
Okay.
And this idea was used to define what it means for a group to be hyperbolic. Basically, a group is hyperbolic if its Cayley graph looks like a hyperbolic space when you zoom out.
Uh-huh.
And this whole notion of hyperbolic groups turned out to be super important.
So they started with pictures of groups, then they zoomed out, and that led them to a whole new kind of group, the hyperbolic group.
That's right. And the source emphasizes that while Cayley graphs are formal mathematical objects, the act of drawing them and thinking about them visually was essential for developing these ideas. Gromov himself, one of the pioneers of geometric group theory, has said that zooming out on Cayley graphs was a key insight.
That's amazing. It really shows how visual thinking can lead to completely new mathematical concepts. Now, in a totally different area, the source talks about visual thinking in mental arithmetic, specifically with people who are really good at using an abacus.
Yeah, those abacus masters are incredible.
They are. So for those who don't know, an abacus is like a counting tool with beads on rods.
Right, and you move the beads around to do calculations. And what's really fascinating is that people who are trained on the abacus, especially the Japanese soroban, can get so good that they can do complex calculations in their heads by visualizing the abacus.
So they have like a mental abacus.
Exactly, and there's a lot of research showing that this is really a visual and spatial skill. Brain imaging studies show that when people do mental abacus calculations, they use areas of the brain that are involved in visual and spatial thinking.
So they're not just doing it symbolically, they're actually seeing the abacus in their mind's eye.
Right. And they make the same kinds of mistakes that people make when they use a physical abacus, which suggests they're really using a mental model of the abacus.
Oh, cool.
Yeah. And they even seem to encode numbers visually. Like if you say a number to them, they might picture it on their mental abacus.
Wow. That's amazing.
And studies have shown that if you disrupt their visual or motor processes, it messes up their mental abacus calculations.
So it's really relying on those senses.
Yeah. But there's a puzzle here because our ability to keep track of individual objects visually is limited, and our number sense gets fuzzier with larger numbers.
Right.
So how can they do these calculations with so many beads?
Yeah. How does that work?
The idea is that they learn to see columns of beads as units, and then they can manipulate those units. And they also use motor imagery, like imagining their hands moving the beads.
That makes sense. So they're not just seeing static images, they're also simulating the movements.
Exactly. It's a very embodied kind of math.
It's incredible how our brains can adapt and use these different senses for mathematical thinking. Now, this brings us back to the big philosophical question of a priori versus a posteriori knowledge. If we're using our eyes and our visual imagination to understand and do math, doesn't that mean maths is a posteriori based on experience?
That's the tricky part. Traditionally, math has been seen as a priori, known independently of experience. But if we're really using our vision, it seems like experience is playing a role. The source makes a distinction between visual experiences that just help us understand things and visual experiences that actually provide evidence for mathematical claims.
Okay, so like seeing a picture of a circle might help me understand what a circle is, but it doesn't prove anything about circles. But if I count 5 objects and then 3 more, and I see there are 8 total, that visual experience is evidence for the fact that 5 plus 3 equals 8.
Right, and the source gives the example of a kid learning addition by counting on their fingers. That's clearly based on experience. And then there's the example of figuring out how many vertices a cube has by looking at a cube or imagining one. That also seems to rely on experience.
So even basic math facts can be learned through experience. Does that mean all math is a posteriori?
Not necessarily. It depends on how strictly you define a priori. If it means only knowable without experience, then yeah, these examples are a problem. But if it means that something can be known without experience, even if there are also experiential ways to learn it, then maybe math can still be mostly a priori.
So maybe there are multiple paths to the same mathematical knowledge?
Right. The source then gives a really interesting example about the proof of the left cancellation law in group theory.
Which says that if you have a group and you multiply 2 elements by the same element on the left, and the results are equal, then the original 2 elements were equal.
Exactly. And when you look at the proof, there's a step where you move brackets around using the associative property. The source argues that seeing those brackets move actually gives you evidence for the validity of that step.
So the visual experience is part of the justification.
Yeah. But then there's the counter-argument that you could write the same proof using a different notation where there are no brackets to move.
Oh.
So maybe the visual experience is just an artifact of the notation, not of the underlying logic.
But the source pushes back, saying that how we understand a proof is tied to how it's presented. And if we're used to seeing brackets, then seeing them move is part of how we validate the proof.
Right. It's like we've learned to trust certain visual manipulations of symbols, and that trust is based on our experience with how those symbols behave.
So even in a very abstract, symbolic proof, there might be elements that rely on visual experience.
It seems that way. Now, what about visual experiences that don't necessarily provide evidence, but are still essential for understanding something?
Okay, like what?
The source gives the example of a square with another square inside it, formed by connecting the midpoints of the sides. If you picture folding the corners of the big square in, it looks like they exactly cover the smaller square,
Right.
which suggests that the area of the big square is twice the area of the small square. And that's actually true.
But they're saying that just seeing that in your mind's eye isn't really proof.
Right. Because our vision isn't perfect, we can't be absolutely sure that the corners fit exactly.
No, it's more like a strong suggestion.
Yeah. But the source says that this visualizing might do something else. It might bring to mind other things we know about math, like the fact that a square is symmetrical.
Oh, I see.
So even though the visual experience itself isn't proof, it triggers these other beliefs. And those beliefs might be justified independently.
So it's like a chain reaction of mathematical thinking set off by a visual spark.
Exactly. And if those other beliefs are true, then this whole process might lead to genuine mathematical knowledge, even though the visual experience wasn't evidence in itself.
That's really interesting. It shows how complex this whole interplay between visual thinking and mathematical knowledge is. Now, finally, the source talks about some other ways that visual representations are used in math beyond proving and discovering things.
Yeah. They mention things like using diagrams in analysis to illustrate how functions change when you apply operations to them, or to show properties like symmetry.
Right. Those can be really helpful for understanding.
And they talk about how visual representations can help us understand why definitions and proofs are the way they are. They even mention a book called Visual Complex Analysis that uses lots of pictures to explain complex analysis.
Sounds cool.
Yeah. And in some areas of math, like geometry and knot theory, the visual representations basically are the mathematical objects.
So you're studying the pictures themselves.
Right. And with computers, we can now make animated visual representations, which can be even more helpful for understanding. They give the example of someone who made animations to explain braid theory.
I'll have to check that out.
Yeah, it's pretty cool. And lastly, the source talks about how visualizations can help us understand the big picture of a proof, the main idea behind it, not just the individual steps. They use the example of Fiske's proof of Schwafel's art gallery theorem.
Which is about figuring out the minimum number of guards you need to watch over an art gallery with a certain shape, right?
Right. And Fiske's proof involves dividing the gallery into triangles, then coloring the corners of those triangles in a certain way. And then you just put guards at the corners with the least common color. And that's guaranteed to cover the whole gallery.
That's clever.
It is. And while you could technically prove this without using diagrams, seeing the triangles and the colors really helps you understand why the proof works.
So the visuals give you the intuition behind the formal argument?
Exactly.
Well, this deep dive has certainly given us a lot to think about. We've seen how visual thinking is involved in proving, discovering, and understanding math. And we've explored the philosophical implications of this for the nature of mathematical knowledge.
Yeah, it's clear that visual thinking is a fundamental part of how we do math, not just a helpful tool. And while we have to be aware of its limitations, it's incredibly powerful for illuminating abstract ideas, finding new discoveries, and even contributing to the logical structure of proofs.
And it makes us rethink the traditional idea that math is purely a priori.
Absolutely. The fact that we can use visual experience to gain mathematical knowledge and even to contribute to a priori insights is really thought-provoking.
So for you, our listener, especially if you're a philosophy buff, this raises a big question. How do we need to change our understanding of math itself to account for this crucial role of visual thinking?
Yeah, it's a question worth pondering.
We encourage you to think about how you use visual thinking in your own life and to explore the sources we've mentioned for more on this topic.
Absolutely.
Thanks for joining us on this deep dive. We hope you've gained some new insights into the amazing connection between seeing and knowing in the world of mathematics.
Thanks for having me.
Until next time.
Bye.
Bye.